Let's say that on a floor, we drag an object of mass, say capital M, by pulling it with a force F star at some angle theta with respect to the horizontal, and this object moves along the floor. So this is kind of like dragging a suitcase, and whether we're moving at constant, we could be moving at constant speed to the right. So let's just say that we're moving at constant speed to sort of mimic being at the airport and pulling a suitcase, so at constant speed. Let's do that. Let's give that speed. Let's say we're moving at constant speed to the right at speed v naught. Now we know the mass of the object. Let's see what ma equals F, what Newton's second law tells us. So if we want to apply this, right, this is a vector equation. Again, the free body diagram can be useful because it breaks up the forces in perpendicular directions. So we have a vertical direction and we have a horizontal direction. Those are the only two interesting directions because the in-out direction doesn't say anything interesting. The in-out component of this says that 0 equals 0. So that's not very interesting. So let's do first a free body diagram. So here is our object of mass m. We pull it out of its environment and we look at the forces that are acting on it. So we know that gravity is acting on this object and its value is capital M times G. That's a known value. We know that there's part of this force, F star, in the vertical direction. And so we have to include that. And so by definition of the sine, which is the opposite over the hypotenuse, we get that there is an F star sine of theta in the vertical direction. And there's another component to the right, which is F star cosine of theta. But there's also the normal force, right? The object isn't falling through the floor, and so there's a normal force to the floor, which we could add here. I don't know how long to make that arrow, but I don't have space, so I'll just leave it like that. So the free body diagram doesn't give us the magnitude. It gives us the direction of the force, and then the magnitude will come out of this law. So let's look at these two components. So let's look at the vertical direction, or y direction. Well, if we decide that this is x and this is y, then y direction, or y component of ma equals f looks like what? Well, the point of the free body diagram is to be able to read off the forces directly, so that's the right-hand side. And on the right-hand side, we see that we have 1, 2, and 3 forces, and one direction they're positive, the other direction they're negative. And our convention is that up is positive, down is negative, but we can change that if we want. But if we follow that convention here, then we have F star sine theta plus the normal force minus mg. That has to equal to the left-hand side. Do we know mass? Yes, so there would be a mass term there. Do we know the acceleration in the horizontal direction? Well, the object is moving at constant speed in the horizontal direction, so that means there is no horizontal acceleration, so this must be 0 in this case. So that's our vertical component, or y direction. The x direction, what does that say? Well, all we have is one force, so it's the right-hand side is straightforward. It's F star cosine of theta. And the left-hand side, if this were correct, the left-hand side would say that there's an acceleration, but that's not compatible with the fact that we're moving at constant speed. So there must be some frictional force here that we didn't put on the free body diagram, right? So you can only go to constant speed if you pull with a force F star cosine theta if there's some friction. And so we don't know anything about the form of the frictional force, but there must be some little f friction. So there must be something like that, and that's the only way that we could get zero. These are equal and opposite to each other. So notice that if we wanted to, say, find the normal force, right, solve for the normal force in this case, we find that it's not equal to mg, but it's a little bit less than mg because part of the F star force, the vertical component of that, is helping us keep the object from going through the floor. And so the normal force is less than that. So that's one thing that pops out of this. And as we said, it must be true that there's a frictional force in this case, which is equal and opposite to the horizontal component of the force of the person that's pulling the suitcase, if that's what this object is. So those are some of the things that come out of F equals ma in this case.